Welcome back to the Deep Dive. Today we are not just scratching the surface. I feel like we're tearing up the floorboards.
We really are.
We're tackling a subject that is effectively invisible to, I don't know, 99% of the population, yet it is the absolute bedrock of our digital reality.
It is. And honestly, today is going to be a bit of a mind bender. We aren't just talking about making the internet faster.
No.
We're talking about changing the fundamental language the internet uses to, to speak.
Exactly. And to kick things off, and the pun is absolutely intended, I want to plant a very specific visual in your mind.
Okay, I'm ready.
I want you to visualize a high-stakes multiplayer football match.
Okay. Are we talking like a Sunday league or the World Cup?
We are talking the World Cup final.
Okay.
But played in a game, like FIFA or eFootball, high fidelity. Millions of polygons.
Right.
You've got 22 players on the field, the crowd is roaring, the grass is rendering in 4K, and you've got the star striker winding up for a massive volley.
I can see it. The tension, the pullback.
Right. He swings his leg. He connects with the ball. It's this blur of motion. Now, freeze that image.
Okay, frozen.
Right at the point of impact.
Yeah.
Usually, when we think about how that image gets from the game server in, say, Frankfurt to your console in San Francisco, what do we think of?
We think of frames, snapshots.
Tick, tick, tick. 60 pictures a second.
Right. That's the traditional video streaming model. You capture the reality of that leg frame by frame, you compress those pictures into a grid of pixels, and you just beam them over the wire. It's a flipbook.
It's a high-tech flipbook, exactly. But here is the twist, and this is where today's topic just completely blew my mind. What if you didn't send the pictures?
Okay.
What if, instead of sending a snapshot of the leg, you sent the math that describes the curve of the leg?
You're talking about moving from pixels to parameters, a totally different level of abstraction.
I am. We are diving into this dense, fascinating research proposal for a new transport protocol. It's called PSTP.
The Parametric Sinusoidal Transport Protocol.
It sounds like a mouthful, I know. But the mission of this deep dive is to unpack why this acronym might just be the future of the metaverse, of low-latency calls, and, well, of gaming. The proposal argues that we need to stop sending raw samples like, WAV files for audio or pixel grids for video and start sending parametric spectral coefficients.
Which basically means sending the instructions for the sound or the motion rather than the recording of it.
It's the difference between mailing someone a frozen cake and emailing them the recipe.
That is a surprisingly good analogy. I like that. If you send the recipe, the receiver can bake it fresh.
Right.
It takes up way less space in the mail, bandwidth, and the cake is fresh when it arrives, no latency.
And that is the big promise here.
Yeah.
We're looking at a massive reduction in bandwidth. The research suggests a 10 to 50 times reduction compared to standard streaming.
That is huge. I mean, just think about that. That turns a 5G requirement into something you could probably run on a 2G network from 20 years ago.
It's insane. But it's not just about saving data. It's about surviving the chaos of the modern internet. So let's get into section 1, the problem setting. Why do we even need this? Why do traditional protocols fail?
To understand the failure, you really have to understand what we call the metronome.
The metronome.
Yeah. Think about how standard protocols like RTP, that's the real-time transport protocol, or WebRTC work. They rely on a heartbeat, a fixed frame clock.
Okay.
If you're streaming audio at 48 kilohertz, the system expects a sample 48,000 times a second, no matter what.
It's a hungry beast. It demands to be fed on schedule.
It does. It assumes synchronous clocking between the encoder, so the person sending the video, and the decoder, the person watching it. It partitions time into these fixed blocks, say 20 milliseconds, tick, tick, tick.
So even if nothing is happening, like if I'm just standing still in the game or holding my breath on a Zoom call, the metronome keeps ticking.
Yes. And the protocol has to send something to fill that silence, or at least maintain the connection state on that grid. It's incredibly wasteful.
But the real world isn't a metronome. That's not how things work.
No, not at all. Real-world signals are event-driven. Think about speech formants, the resonances in your vocal tract that make an A sound different from an E. Or think about that sudden kick in the football game. These things don't change on a fixed grid. They change when they change.
So if I stop moving my character, the game shouldn't need to say he's standing still 60 times a second.
Exactly.
It should just say nothing until I move.
Precisely. Current protocols waste bandwidth just confirming the status quo. PSTP is designed for a chaotic environment. It embraces what the research calls irregular timing.
Okay, let's break that down. The source says updates happen at time t1, then maybe half a second later at time t2, then maybe a tiny fraction of a second later at time t3.
It's not a steady stream, it's bursts. It's asynchronous. There is no strict frame clock synchronization between the server and the client. They're just talking when they need to.
Which sounds liberating, but also, terrifying for an engineer. How do you plan for that?
It gets worse. Or better, depending on your perspective. The research also introduces the concept of variable dimensions.
This was the part that tripped me up initially. I was reading it and I thought, how can the data change its dimensions midstream?
Well, imagine you are describing a sound, let's say a complex orchestral crash, a big cymbal hit.
Okay, big sound, lots of frequencies, lots of overtones.
Right. To describe that mathematically, you might need a vector of, say, 10 coefficients. You need a lot of numbers to capture that complexity.
Makes sense.
But half a second later, the crash fades, and you're left with just a single, pure flute note holding on.
A much simpler sound.
Much simpler. Mathematically, you might only need 8 coefficients, or even 4, to describe it perfectly.
So in a traditional system, I'd still be sending a container big enough for the orchestra, even if it's just the flute play.
Exactly. You'd be zero padding. You'd fill the empty space with zeros just to keep the structure consistent. But PSTP actually shrinks the packet. At time 1, the server sends 10 numbers. At time 2, it sends 8. The data structure itself is shape-shifting in real time.
Okay, so the data structure itself is shape-shifting.
It is. The analogy the research uses is that traditional streaming is a train running on a schedule. It leaves at 8.0, 8.05, 8.0. It doesn't matter if the train is full or empty.
And PSTP?
PSTP is a series of messenger pigeons. You only release a pigeon when you have actual news. And sometimes the pigeon carries a heavy book, and sometimes it just carries a Post-it note.
I love that image. But if I'm the receiver waiting for a pigeon, that sounds like a nightmare to reconstruct. If the pigeon doesn't show up, is it just late or did it get eaten by a hawk?
Or is there just no news?
Right. Or is there just no news? That ambiguity is the massive challenge.
It is, and that leads us to the second big pillar of this research, the signal representation, the language of the pigeons.
Right. If we aren't sending samples, what are we sending? The proposal focuses heavily on something called MFCCs.
Mel-frequency septral coefficients.
Which sounds like something you'd need a PhD to pronounce, let alone understand. So why are these the alphabet of the protocol? What makes them so special?
There are a few key reasons. First, and most obviously, compactness. As we mentioned, you can capture the entire spectral envelope, which is basically the timbre or texture of a sound, with just 8 to 13 numbers.
Versus thousands of raw audio samples for the same duration?
Thousands, yeah. Second, decorrelation. MFCCs are great at separating the source, like the buzz of your vocal cords, from the filter or the shape of your mouth.
Okay, so it separates what's making the sound from how the sound is shaped.
Precisely. And finally, there's perceptual relevance.
Receptual relevance.
The MEL in MFCC stands for the MEL scale, which mimics how the human ear actually hears pitch. We are way more sensitive to differences in low frequencies than high ones. MFCCs prioritize the data that your brain actually cares about. It's an efficient encoding for human perception.
But the sources also mentioned there's a debate here. It's not just MFCCs or bus. There are alternatives. You mentioned LPC and LSF.
This is where we get into the heavy DSP theory, digital signal processing. LPC, or linear predictive coding, is a classic. It's used in old mobile phones. But it has a major flaw for this specific kind of chaotic streaming.
Which is?
Unstable poles.
Unstable poles sounds like a bad day at a construction site. What does that mean here?
In signal processing, it's much worse. An unstable pole means the filter's feedback loop goes out of control. So if a packet gets corrupted or lost, which happens all the time on the internet, the math can literally explode.
Explode.
Theoretically, the values go to infinity. In practice, your speaker emits a deafening digital screech. It's a horrible sound.
Okay, so we definitely don't want that. That sounds like a bug report nobody wants to file.
No. That's why the expert commentary in the source highly recommends LSF, or line spectral frequencies.
Why is LSF safer? What does it do differently?
It has built-in stability guarantees. The mathematics of LSF enforce a rule. The angles representing the filter must always be ordered. So theta 1 is less than theta 2, which is less than theta 3, and so on. They have to stay between 0 and pi.
So they have to stay in their lanes.
Exactly. As long as that order is maintained, the filter is guaranteed to be stable. Even if you have to guess the values between two packets because a pigeon got lost, the result won't blow out the user's speakers.
So it might sound a little weird for a moment, but it won't be dangerous or, physically painful.
Right, it fails gracefully. That seems like a pretty critical feature for a robust protocol.
It does. But let's go back to that shape-shifting data problem, the dimensionality challenge.
Right. The server sent 10 numbers, now it sent 8. How do you compare them? I mean, how do you smooth between a vector of size 10 and a vector of size 8?
My first thought is you just chop off the last two numbers, but that seems really abrupt.
It is. And the naive solution is zero padding. You'd add 2 zeros to the shorter vector to make them the same size. But that causes artifacts, clicks, pops. It sounds like the audio is stuttering.
So what is the recommended approach in PSTP?
Something called energy-weighted projection.
Which sounds incredibly sci-fi. How does that work?
It's fundamentally about conserving physics. You treat the coefficients as projections onto a mathematical basis. When the dimension drops, when the number of coefficients, kt, decreases, you have to redistribute the energy of those lost dimensions into the remaining ones.
So the signal doesn't just suddenly get quieter or smaller. You're preserving the energy.
Exactly. You maintain energy conservation. The equation logic, which is basically CMT2 should be approximately equal to CAT2, ensures that the total power of the signal stays consistent even as the description changes shape.
It's like pouring water from a wide, shallow glass into a tall, narrow glass. You don't want to lose any of the water. You just want it to fit the new container.
That is a perfect analogy. The volume, or in this case the energy, stays consistent.
Now, there's one more elephant in the room regarding MFCCs and these kinds of representations. The phase problem.
Ah, the classic trade-off. MFCCs describe the magnitude spectrum, so how loud each frequency is, but they completely discard the phase, the timing alignment of all those sine waves.
And without phase, you lose the crispness of the sound? Is that what happens?
You lose the temporal structure. A voice can sound smeary or robotic. The attack of a drum hit gets lost. The standard fix for this is an algorithm called Griffin-Lim.
Okay.
Which is basically an iterative guessing game. It looks at the magnitude and tries to guess what the phase should be over and over again until it sounds right.
But guessing takes time. That sounds slow.
It is. It can add 50 to 200 milliseconds of latency. In a real-time protocol, that's an eternity. If you're playing a competitive game, 200 meters is the difference between winning and losing.
Absolutely. So what does PSTP do? It can't afford to wait.
It uses a parametric phase model. Instead of guessing, it transmits an extra parameter called group delay along with the MFCCs.
So it adds a tiny bit of data 1 extra coefficient to save all that processing time.
Exactly. It guarantees deterministic phase without the wait. It turns a long, iterative guessing game into a simple, one-shot calculation.
Okay, so we've got our alphabet, these variable-size, stable vectors arriving via pigeon, but now we have to string them together. This brings us to section 3, temporal modeling.
This is moving from dots to lines. The client receives these sparse updates. These are the dots on a graph. It has to connect them to make a smooth, continuous wave.
And the source says the core concept here is that the client isn't just playing samples. It's simulating a continuous dynamical system. What does that mean?
That's the big paradigm shift. The client is running a simulation. It's almost like a little physics engine. It has a model of how the signal is supposed to behave. The updates from the server are just nudges. They're observations that correct the simulation and keep it on track.
So how do we connect the dots? The simplest way, I assume, is just linear interpolation.
Drawing a straight line between point A and point B.
It's a low latency, but I'm guessing it sounds bad.
It sounds robotic, and it creates sudden changes in direction. Imagine a car driving down the street. To turn a corner, it has to curve smoothly. Linear interpolation is like the car stopping dead, rotating 90 degrees on the spot, and then driving forward again.
It's jerky, unnatural.
And in audio, that jerkiness causes audible clicks. In animation, it looks like a glitch. The character model just snaps to a new position.
So we need something smoother. The next step up is the cubic Hermite spline,
which adds the concept of velocity to the points. It doesn't just know where the points are, it knows the direction they were heading. It smooths out the corners.
Okay.
It gives you what's called C-in-01 continuity, meaning the speed doesn't jump around. But to do it perfectly, you often need to look ahead one packet.
Which adds latency.
Yeah.
You have to wait for the next pigeon to arrive to know how to properly curve the line to the current one.
Right, you're always one step behind. So for the absolute best result, PSTP proposes the gold standard, the Kalman filter.
I feel like Kalman filters are the answer to everything in engineering, from rockets to stock markets to this.
They essentially are. They're incredibly powerful for estimating the state of a system with noisy or incomplete data. The Kalman filter uses what's called a state space model. It has two simple steps: prediction and update.
Walk us through the prediction step. What's the filter doing?
In between packets, the client is just guessing where the signal is going. It uses a transition matrix, mathematically represented as fidda.nado xPAE, to project the current trajectory forward into the future.
So even if no packet arrives, the Kalman filter just keeps drawing the line. It just keeps going.
Exactly. It handles jitter naturally. If a packet is 20 milliseconds late, the filter just keeps predicting for an extra 20 milliseconds based on the physics model it has. It doesn't stutter, it just extrapolates smoothly.
And then the update step.
When the pigeon finally lands, when the packet arrives, the client says, aha, my guess was slightly off, and it corrects its path. But it does so smoothly, it averages its prediction with the new data, minimizing the error.
This connects to the Wiener filter logic mentioned in the math section, right? Minimizing the mean squared error.
Yes, that's the core mathematical principle. It's trying to estimate the true underlying curve from these sparse, noisy observations. It's optimizing for smoothness and energy continuity. It fundamentally assumes the real world is smooth, not jerky.
So the client is essentially hallucinating the signal in a mathematically rigorous way, and the server just checks in occasionally to make sure the hallucination is still accurate.
That is a surprisingly accurate description. It's a controlled hallucination.
I love it. Okay, let's get into the nuts and bolts. Section 4, protocol design, the actual transport layer. How are we packaging this information?
We're using a binary little endian format. Efficiency is absolutely key here. Everything is stripped down.
And the proposal mentions something called delta encoding.
Right, this is a classic compression trick. Imagine I need to send you the numbers 100, then 101, then 102, then 103. In a raw format, I send those four big numbers. In delta encoding, I send 100. Then for the next packet, I just send +1. And the next is +1, and the next is +1.
Much smaller data.
It can reduce the bandwidth for slowly changing parameters by 50 to 70%. Combine that with sparse encoding, where you only send the coefficients that actually changed, and you're stripping away almost all the redundancy.
Now, we talked about the messenger pigeon timing and the clock problem. The server and client have different watches. They're not synchronized.
This is the bane of distributed systems, clock drift. If my second is slightly shorter than your second, eventually the audio will start to skip or the buffer will run dry.
How does PSTP fix it?
It relies on tight integration with something like IE 1588 PTP, that's the Precision Time Protocol, or even just a well-implemented NTP. But more importantly, on the client side, it uses an adaptive jitter buffer.
How is that different from a normal buffer?
A normal buffer is fixed. It says, I will always wait 50 meters before playing. An adaptive buffer watches the network. If the network is jittery, if the variance in packet arrival time is high, the buffer grows to prevent gaps.
So it adds a bit more delay to be safe.
Right. And if the network is stable and fast, the buffer shrinks to reduce latency. It targets a packet arrival probability of greater than or equal to 0.99.
It wants to be 99% sure that data is there before it tries to play it.
Exactly. It plays it safe when the weather is bad, and it plays it fast when the weather is good.
But what about the disaster scenario?
Yeah.
Packet loss. The pigeon gets shot down. The data is just gone.
The first line of defense is forward error correction, FEC. Specifically, something like Reed-Solomon codes.
Okay, can you explain that simply?
It's like sending extra puzzle pieces. If you have a 10-piece puzzle, I actually send you 12 pieces. The extra 2 are mathematically generated repair pieces. If you lose any 2 of the original 12, you can still use the others to reconstruct the full picture.
So you can recover from a certain amount of loss?
Right. A common setup is RS-1210, which allows you to perfectly recover from 2 lost packets in a block of 12.
And if you lose 3, if the loss is worse than you planned for?
Then the math fails, and we fall back to the second line of defense, prediction-based concealment. Remember the Kalman filter?
The controlled hallucination.
Yes. If the packet is truly lost and unrecoverable, we don't play silence. That's jarring. We let the Kalman filter guess the next 50 milliseconds based on the trajectory it was already on. We might even flag that audio or motion as low confidence, but it's almost always better than a gap of silence.
It effectively bridges the gap with a best guess extrapolation.
Exactly. It's all about failing gracefully.
This is incredibly robust. It seems to have an answer for everything. So we've got this powerful engine. What can we do with it? Let's talk about Section 5, real-world applications. And we have to start with the FISA example because that's just so cool.
Gaming and animation. This is a massive, massive data problem. Consider that multiplayer football game. You have 22 players. Each player has a skeleton with maybe 30 joints.
Knees, elbows, hips, spine, neck.
Yeah. And each joint has a rotation, which is usually described by a quaternion. That's 4 values per joint.
So 30 joints times 4 values, that's 120 numbers per player, 60 times a second. That adds up fast.
It does. The raw data cost is around 634 kilobits per second for the whole match. That sounds okay on fiber, but on a shaky mobile network, that's lag city. Your game is unplayable.
So how does PSTP fix FIFA? How does it apply?
It treats the motion of the leg just like a sound wave. It decomposes the motion into frequency bands using spectral encoding.
Wait, so you're telling me running is a low frequency?
Exactly. Think about it. Running is rhythmic. It's a loop. Your legs go back and forth in a predictable way. That's a long frequency wave, maybe 1 to 4 hertz.
Okay, that makes sense.
What about a kick?
That's a quick motion, sudden.
It's a high-frequency transient, a sudden spike in the data.
So you only transmit the notes that the body is playing at any given moment.
Correct. You transmit only the significant modes. You use sparse updates. If the player's just running, you ignore the high frequencies because nothing is happening there. You only send the 1 or 2 coefficients describing that low-frequency run cycle.
And the numbers. What's the bottom line on bandwidth?
The source claims you can drop from an average of 28.8 kilobps per player down to 1.44 kilobps. That is an 85% reduction, or even more.
That is game-changing. Literally. Yep. That's the difference between a game being available on mobile or not.
And because the client is using that smoothness constraint we talked about, the Kalman filter, the motion looks fluid, even at that ridiculously low bitrate, no jittery players teleporting around the field.
What about beyond gaming? The proposal mentions haptics.
Haptics is touch. Imagine telesurgery, or even just VR. The surgeon needs to feel the resistance of the tissue. Your VR controller needs to simulate the texture of a surface. That resistance, that texture, is a waveform.
And PSTP can transmit that waveform super efficiently.
Exactly. Or think about biomedical applications.
Like an ECG monitor.
Yeah, an ECG. Your heart rhythm is largely repetitive. Beep, beep, beep. Why send the same bump data continuously from a wearable device? With PSTP, you only transmit when the rhythm changes spectrally, which might indicate a problem. It saves battery and bandwidth.
It's efficient. That seems to be the core value here.
It's efficiency and resilience, hand in hand.
So let's look at the destination, the final part of the journey, Section 6, the client reconstruction pipeline. The packet arrives. What happens? Step by step.
Okay, so it's a 5-step factory on the client side. Step 1, receive. The packet arrives with a timestamp and that sparse vector of coefficients.
Okay, pigeon has landed.
Step 2, model update. We feed that new data into the Kalman filter or the spline state. We update the physics of our simulation. We correct our trajectory.
So that we adjust our controlled hallucination.
We do. Step 3, interpolate. This is crucial. The server might send updates every 50 milliseconds, but the audio hardware needs data every 10 milliseconds, or even more frequently. The client generates the dense parameters for all the frames in between the updates.
Filling in the gaps smoothly.
Exactly. Then step 4, synthesize. We convert those LSF or MFCC numbers back into something we can use, like a magnitude spectrum or LPC filter coefficients. We generate the excitation, the source buzz or noise, and apply the filter to it. We're baking the cake.
And finally, what's the last step?
Step 5, overlap add. You can't just stick the chunks of audio end to end, you'll hear clicks. So you blend them using something like a Hahn window. This ensures there are no audible seams between the chunks. Perfect reconstruction.
That's a pretty complex pipeline. How do we know it's working well? What are the metrics for success?
Well, we measure 2 main things, latency and quality. For latency, PSTP targets 30 to 50 milliseconds end-to-end.
How does that compare?
That's comparable to OPUS, which is the industry standard for VoIP, like on Discord or Zoom, but PSTP does it at much, much lower bitrates.
Okay, and quality. How do you measure good?
We use a couple of standard scores. One is PESQ, that's the perceptual evaluation of speech quality. The other, which is more technical, is LSD, log spectral distortion. It basically measures how far, in decibels, the reconstructed spectrum is from the original. The target for high quality is an LSD of less than 2 dBs.
So, low latency, high quality, tiny bandwidth. It sounds too good to be true, but the math seems to back it up.
Ideally, yes. The trade-off is complexity. You are shifting the burden from the network to the CPU. The client has to be smart. It's not a dumb player anymore.
Which brings us perfectly to the future. Section 7. Where does this go next? If the client is already smart, how much smarter can it get?
Well, the next logical step is the neural frontier. We talked about Kalman filters being the brain of the client.
Right.
But what if we replace that mathematical Kalman filter with a literal neural network, like a GRU or an LSTM?
Hybrid approach?
Exactly. You use a lightweight neural network on the client to predict the next packet. AI is incredibly good at predicting sequences. It could learn the specific way a player tends to move or the specific cadence of a person's speech and predict it far better than a general-purpose math filter.
You could even use generative models for it.
Absolutely. You could use something like Google's Lyra or Meta's encodec. You'd transmit the parameters for a decoder network using PSTP's efficient transport logic. The network on the client then hallucinates the audio based on those super compact parameters.
And there's a fascinating note here on privacy and security that I did not see coming.
This is a really interesting side effect of parametric streaming. Since we aren't sending your actual voice, we're sending parameters describing your voice. We can manipulate them in transit.
You mean like voice anonymization?
Precisely. We can shift the F0, which is the fundamental pitch. We can smooth the vocal tract formants. We can remove the unique identifiers in your voice that make you sound like you, while keeping the words and the intonation perfectly intact.
So I could sound like a generic human, but still convey the same emotion and meaning.
Exactly. Or, even more securely, we could use something called homomorphic encryption.
Whoa, okay.
This allows a server to process the parameters without ever decrypting them. So the server can mix audio streams or apply effects, but it never actually knows what you're saying. It's processing encrypted data.
That is huge for security. I mean, truly private communication.
It really is. It opens up entirely new ways to build secure communication systems.
So let's wrap this all up. After this whole deep dive, what is the final takeaway for our listener? What's the big picture?
PSTP and concepts like it represent a fundamental shift. We are moving from sample-based streaming to model-based streaming.
Decoupling transmission time from playback time.
Yes, we are no longer slaves to the frame rate. We are no longer on the metronome's schedule. We are sending the instructions, not the finished product.
It's a provocative thought. The source material ends with this idea that as we move into the metaverse and the haptic internet, maybe we start sending data in the traditional sense. Maybe we start sending equations describing reality.
That's the future. Don't send the world. Send the math that builds the world on the other end.
Sending the DNA of the signal rather than the body. It's so elegant.
It's the only way we'll be able to scale to the complexity of the digital worlds we want to build. The old way just won't cut it.
I want you all to think about that next time you see a glitch in a video game or hear a stutter on a Zoom call. Think about the messenger pigeons that didn't make it and the math that could have saved them. Thanks for diving deep with us.
A pleasure, as always.
See you on the next one.